Okay, so I want to go through with this lecture and introduce two equations. You got the focal length equation on the left. You have the Lensmaker equation, approximation equation. That's why I have this approximation symbol here. It's not exactly equal, but it's a great approximation. So we want to first talk about what these letters mean, these variables mean, and then do some sample problems so you can get some practice doing this. So F is equal to the focal length. So if you're taking light from far away, so for example, if you have a lens, converging lenses, this light's coming from far away, it's going to focus at some point. That's that focal point. Every lens, every set of glasses or anything like that is set with a focal point. Your eye has a focal point. We talked about that in the last video. That focal point can either be on the retina, in front of the retina, or behind the retina. So that focal point O is equal to the object distance, or how far the object is from the lens. Okay, and then the I is equal to the image distance. And this is how far the image is from the lens. Oh, and this could also be mirrors. So let me add that in there. So lenses or mirrors. The equation works the same for lenses or mirrors. Obviously, the Lensmaker equation is only going to work for glasses or lenses, but the focal length equation works for both lenses and for mirrors. Sometimes you'll see this equation written in different forms. You'll see as 1 over f is equal to 1 over di plus 1 over do. I was taught with O and I, so that's kind of like where I like to stay with that. Same equation, just different letters. Again, f here is your focal point. N is equal to the index of refraction. And so this depends on the material. And what do I mean by index refraction? So if you think about it, you have a cup of water and you put a straw in it. The straw appears to bend. Okay, in reality, the straw doesn't bend, but it appears to bend when you look at it through water. If you've ever played in a pool, you know when you put your quarter game in it, your quarter at the bottom of the pool and you dive in, it's not where it appears to be because light bends. It's how index refraction is basically a measurement of how light is going to bend as it passes through it, how sharply it's going to bend or how weakly it's going to bend. So different materials, different types of glass, different types of plastic, all have different index refractions. And so when someone's designing glasses, they will take that into consideration for those glasses. And then R1 is equal to the radius of the side of the object. And then R2 is equal to the radius opposite the object. So what I mean, if I'm looking at a tree, and I have my glasses here, so this is R1, the side of the lens closest to the object, so it's going to get the light from the object first, and then R2 will be the side opposite the object on the other side. Now, I would say image, but the image can be in multiple places, okay? So we're going to go through and use these. Let's look at these equations. So I want to first look at, if I put a tree here, and I want to have a converging lens, and I want to have a focal length for the converging lens to be 10 centimeters, and I'm going to put the tree 40 centimeters away. I know these, well, let's change these to meters, so it's a little bit more realistic. I want to find focal point, or sorry, not find, I want to find the location of the image. Okay, so I have a lens that has a focal point of 10 centimeters. I have a tree that's 40 meters away, and I want to find those. So we can just plug and chug numbers in. So we have 1 over f is equal to 1 over O plus 1 over I, and I'm trying to find I. So let's put in 1 over 10 is equal to 1 over 40 plus 1 over I. So remember I said you review fractions because this is the fun part. So I have 1 over 10 minus 1 over 40 is equal to 1 over I. And I know you want to grab the calculator, but hang with me for a little bit. We have a common denominator of 40. So I have 4 minus 1 is equal to 3 over 40 is equal to 1 over I. Now this is where people have problems with the algebra. I need to flip this whole thing. So I is equal to 40 over 3. So I'm flipping both fractions here. If I take 40 over 3, I get 1.33333. I'm sorry, 13.3333. So my I is equal to 13.33 centimeters. Now this is where optics gets a little crazy. This is a positive I. And so it is actually real. So let me back up here. So this is real. So it's where light should go. So light should pass through the lens. So my image is 13 centimeters away. And without going into a lot of the physics, here's going to be my image. So my image is going to be on the opposite side, upside down. You're like, well, how do we know it's upside down? Well, my magnification equals negative I over O. Let me write these out so you can see this. So M is equal to negative I over O. So I have a negative 13.33 over 40. So my magnification is equal to a negative 13.33 divided by 40. And I get a magnification of negative 0.333. So what that means is one item, this right here, is less than 1, so I'm smaller. And this is negative, so that means I am inverted or upside down. So I have an image that is upside down and it's smaller. It's actually 1/3 the size, so I made it a little bit too big. So we got using the equation, so you can look at if it's real, positive, it's where it should be. So let me do one where it's going to be a little bit different. So let's take the same tree. I have a lens here, so our F is equal to 10 centimeters, and let's put our tree at 5 meters. Okay, so this is our object distance, and there's our focal point. So I have 1 over F is equal to 1 over O plus 1 over I. So that's 1 over 10 is equal to 1 over 5 plus 1 over I. Take that 1 over O over. So I have 1 over 10 minus 1 over 5 is equal to 1 over I. So common denominator is 10. So I have 1/10 minus 2/10, which is a negative 1/10, is equal to 1 over I. And I need to flip both sides. So I have a negative 10 over 1 is equal to I, or my I is equal to a negative 10 centimeters. So now this negative means that I have a virtual image. So it's where light should not go. So for a lens, the light should go through, correct? So I would have real over here, but what happens is now light goes back. So if this is 5, my tree is here. If I have a virtual image, my light has gone backwards, which is not what it should do. And my magnification is equal to negative I over O, which is equal to a negative 10 over 5, and that is equal to 10 over 5, which is equal to 2. So it's positive, so it's upright. And now this 2 is greater than 1, so it's 2 times bigger. So now I'm upright, and I'm 2 times bigger. So this is my image here. Okay, and I'll give you some more practice on problems as well, so you can go through and look at what things mean and so forth. And then if you're using the Lensmaker equation, it's really just going to be plug and chug as well. So let's say that, let me scroll back down here. I have 1 over F is equal to N minus 1 times 1 over R1 minus 1 over R2. And let's say that I have a set of glasses with N equal to 1.4. And my radius 1 is equal to 10 centimeters. And my radius 2 is equal to 5 centimeters. Okay, so what is my focal point? So now it's really, for these types of problems, I'm going to have to give you the values, and it's really just plug and chug. There's not a whole lot of interpretation. So I have 1 over f is equal to 1.4 minus 1 times 1 over 10 minus 1 over 5. Now note we have things in centimeters, so keep that in mind. Our distances are in centimeters. So I get 1 over f is equal to 0.4 times 1 over 10 minus 2 over 10. 1 over f is equal to 0.4 times 1/10 and negative. And so 1 over f is equal to 0.4 negative over 10. Flip both sides. So f is equal to negative 10 over 0.4. So when you multiply those numbers, or sorry, divide those numbers, I get focal point equal to negative 25 centimeters, because that's where the problem was coming in. And negative means I have a diverging, the glasses are going to act like a diverging lens together. Okay, so this negative means I have a diverging set of glasses. Now they're not, it's not going to look like this, because remember that's going to be hard to put on the eye, but they're going to do the same thing as those glasses would do. So this person would need a prescription of a focal point of negative 25 centimeters. Okay, so again, I'll give you some more practice. In the next video, we'll look at kind of a basics on microscopes and telescopes. I'll probably actually upload some videos so you can see some images and see some better images of how we use these microscopes and telescopes with the same principle that we're doing right here.